Hi everyone! This video looks at a weak base titrated with a strong acid and will focus on the pH calculation before the equivalence point, which is called the buffer zone. If the titrant volume in the problem is more than 0 milliliters, then we have to set up a millimole table. The E row of our millimole table tells us where we are on the titration curve and guides us as to how to calculate the pH from that information. There are many different generic notations for a weak base depending on the source. I choose to use a consistent notation of A- for a conjugate base. Many weak bases are not ions, so that is one tiny glitch with this approach. It is possible that the charge of A- may not align with the actual charge of the weak base. I do feel like it's easier to keep track of what's going on if we use the same generic notations consistently throughout all of these titration and equilibrium problems, rather than switching back and forth. In this sample millimole table, we are only looking at the E row. Here we see that H+ is used up, and that the solution contains both the conjugate base A- and the conjugate acid HA. Whenever we have a solution containing both conjugates, we have a buffer. This means that our reaction progress is in region 2 of the titration curve, which is called the buffer zone. A- and HA can be any values as long as they are both greater than 0. Here, we'll look at the situation where they are not equal to one another. Because we have both A- and HA, we can use the Henderson-Hasselbalch equation, which is pH equals pKa plus the log of the conjugate base over the conjugate acid. It is important to continue to use this form of the Henderson-Hasselbalch equation, even though we started with a weak base. You only have to recognize that we likely have Kb or pKb information given in the problem, and we'll have to calculate pKa for the conjugate acid. The other thing about this equation is our log term is a ratio, A- over HA. And that means we can use any units as long as they're the same. In this example, we can plug in millimoles directly and don't need to calculate molarities first. Just be careful to ensure that the conjugate base is in the numerator and the conjugate acid is in the denominator. Because their locations are different in the weak base millimole table compared to the weak acid millimole table, there's a tendency to accidentally invert the log term. The first thing we notice in our example is that our titrant volume is greater than 0 mils. That means we need to set up a millimole table. The reaction at the top of our millimole table is the conjugate base A- reacting with H+, the titrant, to form the conjugate acid, which is A-. The rows are initial, change, and end, and our units are millimoles. We need to calculate the millimoles to enter into this table. So we'll start with A-. We have 20 milliliters of solution. Make sure you're including all the zeros so the sig figs get noted correctly. We'll multiply that volume by the molarity of our A-. Our A-, again, is the notation that I'm using for the conjugate base. So the molarity of that is 0.02920 moles of A- over liters of solution. Liters of solution will cancel, and we'll be left with milli and moles. Taking a look at our sig figs, we have 4 sig figs in our volume, 4 sig figs in our molarity, so our millimoles will be rounded to 4 sig figs. Doing the calculation, 20.00 times 0.02920 rounded to 4 sig figs gives us 0.5840 millimoles of A-. For our titrant, H+, We're starting with 11.23 milliliters of solution multiplied by its molarity, which is 0.04000 moles of H plus per liter of solution. We cancel liters of solution. We're left with milli and moles. And now we take a look at our sig figs. We have 4 sig figs in our volume, 4 sig figs in our molarity, and so our millimoles will also be rounded to 4 sig figs. Doing the math, 11.23 times 0.04000 rounded to 4 sig figs gives us 0.4492 millimoles of H plus. We can enter those values into our table. So for A minus, 0.5840, H plus 0.4492, and HA we start with 0. We subtract the smaller value from each reactant, which is the 0.4492, so minus 0.4492 and minus 0.4492 for both the A minus and the H plus. On the other side, we have to add that same value, 0.4492, for our HA. The H plus will go to 0. The HA will be at 0.4492. And we'll calculate our A minus, 0.5840 minus 0.4492. This is subtraction, so our sig figs will be rounded to the fewest decimal places. They're the same, so 4 decimal places will give us 0.1348 millimoles. At this point, we evaluate what the E row is telling us. And the E row is telling us that we have both A minus and HA in solution. And whenever we have both conjugates, a conjugate acid and a conjugate base, or a conjugate base and a conjugate acid, we have a buffer. So for this titration, we are in the buffer zone. Because we have a buffer, we can use the Henderson-Hasselbalch equation, which is pH equals pKa plus the log of the base term A minus over the acid term HA. Now we can plug the values from our E row directly into the log term. The information we're missing here is pKa. There are different paths we can take to get from Kb to pKa. I will go ahead and go from Kb to Ka and Ka to pKa. So to go from Kb to Ka, I will use the equation Ka times Kb equals 1.0 times 10 to the negative 14. Rearranging that equation, Ka equals 1.0 times 10 to the negative 14 divided by Kb, which will give us 1.0 times 10 to the negative 14 divided by 1.7 times 10 to the negative 5. Looking at sig figs, we have 2 sig figs in each value, so our Ka will be rounded to 2 sig figs. Doing the math, 1.0 times 10 to the negative 14 divided by 1.7 times 10 to the negative 5 rounded to 2 sig figs gives us 5.9 times 10 to the negative 10. To calculate pKa, now we can just take the negative log of that. So pKa equals negative log of 5.9 times 10 to the negative 10. The 2 sig figs in our log term will become 2 decimal places in our result. So taking the negative log of 5.9 times 10 to the negative 10 gives us 9.23 for our pKa. Now we can plug everything into the Henderson-Hasselbalch equation. So I'll come back up here where I have this equation written. pKa is 9.23 plus the log of A minus 0.1348 divided by HA 0.4492. We'll have 9.23 plus the log term. So for the log term, we have 4 sig figs in the numerator and in the denominator, which means after we do that math, we'll round that to 4 decimal places. 0.1348 divided by 0.4492, and taking the log of that to 4 decimal places gives us 0.5227. Now when we do this final addition, our sig figs will be determined by the 2 decimal places in the pKa because that's the fewest number. So our last step is to add those 2 numbers together. 9.23 plus 0.5227 rounded to 2 decimal places gives us 9.75.